Rocket Science, Part 2, Using Numerical Integration. This is a lesson based on Tips on Physics by Richard Feynman. Recall from our previous video that the system we defined is both the rocket and the fuel. So we have a separate mass for rocket and separate mass for fuel. And a rocket travels by having equal and opposite momentum on the mass of the rocket and opposite mass of the fuel. And we can write those equal and opposite impulses as change momentum. The mass of the rocket changes its velocity. And what's the impulse on the mass of the fuel? Well, for simplicity, as we learned in the last lesson, and what's close to actually done, the velocity of the fuel, the exhaust velocity, is kept nearly constant for simplicity. And so that means the change in the momentum is not a change to the velocity, but a change to the mass of the fuel. So our velocity of a rocket can be written algebraically as a ratio of the change in mass of the fuel over the mass of the rocket times the velocity of the fuel, treating the velocity as a fuel as a constant. And that change in mass of the fuel is the opposite, is the loss of the mass of the rocket. Negative delta, sans minus the loss of the rocket's mass, becomes the fuel that gets ejected with an equal and opposite impulse. Now, the mass is really continuously distributed, or continuously lost or dropped out. So we can change the deltas to infinitesimals, dv and dm. And then we can rearrange to find the velocity of the rocket by the techniques of integration. But what if we don't want to integrate, or we don't want to use the tools of integration, or we don't know what the answer to the integral is? Is there another method? Well, that's where numerical integration comes in. Numerical integration is a way of summing up values to approximate the result that you get by summing up infinite amount of continuously changing variable in integration. So computers don't integrate continuously changing values. Learn how to do numerical integration is a good trick for programmers. We can approximate an integral as precisely as we like, as long as we're summing up changes of continuous values, treating them as discretely, just more and more precisely. How do we do that? So the velocity of this rocket we know relates to an integral, but we're going to try to approximate that integral to get the velocity of the rocket after some time as the mass of the fuel has been ejected. So our change in velocity of the rocket relates to the ratio of the mass ejected per the overall mass of our system, the mass of our rocket. The mass of the rocket will decrease as the mass of the fuel gets deposited or gets ejected out. So let's say our mass of our rocket is 100 units of some mass. And let's say that mass of the fuel, that delta M that got ejected out, is 10. So we're going to add steps of 10. We're going to inject mass of 10, and then another mass of 10, and another mass of 10. So our mass of our rocket will reduce from 100 minus the mass of the fuel to 90 to 80, etc. So we'll do 10 steps. The mass of the fuel will be ejected out in 10 steps. So after the fuel of 10 has been ejected, our rocket now has a mass of 90 minus that 10. And so our ratio of 10 change in mass divided by the mass of the rocket, which is not 100, it's 100 minus 10, the mass that it's lost, so 10 over 90, which is the same thing as saying 1/9. So after ejection of 1/10 of the mass, we have that ratio as 1/9. Again, what we're trying to do here is that in that part in the brackets, we're trying to approximate that value without having to the integral. This is how we're learning how to do numerical integration. We're going to treat that integral as a sum of this delta M over M, rather than an infinite sum, rather than integration of dm over M. But what we just did wasn't quite right, because the mass is continuously being ejected out. So it's not this 10 just gets dropped out immediately. That 10 gets shot out over some time frame. And the mass doesn't go down to 90 the mass of the rocket doesn't go down to 90. The inertia of the rocket is at 90 until the full mass of the fuel, until the full 10 gets ejected. It's getting reduced into the last instant to be 90. So to get a better approximation, we should divide that delta M by 2 as that mass is getting ejected. On average, the mass of the rocket during that period of the mass of the fuel being ejected is 95, or half of that mass is being ejected and half is still waiting to be ejected. So it's 95 would be the inertia of the rocket during this ejection of the mass of the fuel. So over that time frame, that's how much we first have ejected in these chunks. So our ratio becomes 1 over 9.5. Again, we're trying to approximate what this in the bracket is without having to integrate. So in the next time chunk, we eject another 10. And so now we've reduced the mass of rocket. 10 has been ejected, but over that time frame that the 10 has been ejected, half is in and half is out. So on average, our mass of our rocket, the inertia of the rocket is 85 as that 10 gets ejected until finally it's the mass of the rocket goes from 90 to finally down to 80. So 10 over 90 minus 5, or 10 over 85, gives us, of course, 1 over 8.5. And on we go. We eject another 10 to reduce the mass of the rocket from 85 to 75. And while that mass of the rocket is being reduced from 85 to 75, we should again take the average, 80 minus 5. So the average mass of the fuel that's being ejected over that chunk of time is 5. And so we're down now to a ratio of 1 over 7.5. And on we go. So the sum of that ratio, the mass being ejected per the mass of the rocket, as the mass of the rocket is changing while it's being ejected, would be these fractions until we eject all 10 parts of that mass until we're left with no mass of the rocket. What are those fractions? 1 over 9.5 plus 1 over 8.5. What does that all sum to? Well, check the numbers and you'll see it adds up to just two snippy digits, 2.3. Well, how do we do? That ratio is 2.3, and we're trying to approximate that with the integral in the brackets there. We're saying then the velocity of the rocket after the mass is ejected is now 2.3 times greater than the velocity of the fuel. We've ejected in 10 steps a mass of 10 a tenth of the mass is getting ejected in 10 steps, or 10% at a time. And so the end of that ejection of the fuel with our less mass into the rocket now, the velocity of the rocket with its less mass as the fuel has been injected from those impulses is now 2.3 times greater than the constant velocity of the fuel. Well, again, we approximated this integral. Let's look at that integral. You know that this integration here, we start out our initial mass is 10. We work our way from 10 to 20 up until 100, so we're doing 10 steps. And so what is this integral? Well, dm over m, or dx over x, is a natural log of these 10 steps, changing by 10 each time. And so what's the natural log of 10 to two significant digits? It is 2.3, so we approximated using this technique of numerical integration without doing a continuous change, without doing integration. We've got the value to two significant digits. If you want to go out to 3 or 4 digits and check the precision, you'll see we're a little off. But you can be more precise rather than ejecting 10 at a time, or 10%, or 1/10 at a time. You can eject 1%, or 1,000th of a percent, or 1 over a million. The delta M can be as small as you like, and the more precise you'll be to approximate this ratio. This is how we can approximate the answer to any old integral, simply using arithmetic.